Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to look at Newton's method in n dimensions. So in this topic, we will derive Newton's method in n dimensions, and we will observe that the formula we find is analogous to the one we've already seen, that is, the one where we apply Newton's method to find the root of a single nonlinear expression in one variable. We'll look at an example, and we will observe that the rate of convergence is still order h squared. So one last review of Newton's method. Given an approximation to a root, we get a better approximation of the root by finding the root of the tangent line at x sub k, f evaluated at x sub k. All right, recall the Taylor series for a real valued function of a vector variable. So f at u is equal to f at u naught plus the gradient inner producted with u minus u naught. Now I'm going to write this slightly differently. I'm going to write this as the value of the function plus a 1 by n matrix, which is has the entries of the gradient multiplied by the difference u minus u naught. Well, if we have n such functions, then for each we have exactly this same expression. Thus we have this system of n equations. Everything on the left-hand side, therefore, could be interpreted as a vector of n values of those n functions evaluated at u. Here we have a vector of the n functions evaluated at u naught. And this is a matrix now times u minus u naught. It's an n by n matrix times the difference of the vectors u minus u naught. Thus we now have this vector matrix equation. So the left-hand side is the vector valued function of a vector variable, f at u. Here we have that f evaluated at the vector u naught. And that matrix is the Jacobian, or it's called the Jacobian, evaluated at u naught. So we see the Jacobian down there, and that Jacobian matrix is multiplied by the difference u minus u naught, which is a vector. I believe you have seen the Jacobian in your first year calculus course. All right, so in this we now have n tangent n minus 1 dimensional hyperplanes at u naught. A root of this hyperplane may be found by equating this to 0. Now that requires us to bring f to the other side. We'll negate it, and now we have the Jacobian times an unknown step size equaling the negation of f evaluated at u naught. This is a system of n linear equations in n unknowns which we can solve. Now, for simplicity, let's just let delta u naught represent the difference between u minus u naught. So there is the actual system which we're going to solve, and we will solve it for delta u naught. Having found delta u naught, we define u1 to be u naught plus this delta. That is our next approximation of the root of this vector valued function of a vector variable. We can now repeat this until the 2 norm distance between two successive iterations is sufficiently close, and the 2 norm of the function evaluated at this new point is also sufficiently small. All right, You may be wondering, how are these in any way related? On the left-hand side, you saw Newton's method, and that is what you learned in your first year calculus course. Now I'm telling you that we must calculate the Jacobian and solve the Jacobian times delta UK equaling the negation of f evaluated at UK. We solve that for delta UK, and thus we assign UK plus 1 to be the previous value plus this delta UK. The two seem to have nothing to do with each other. Well, let's go back to Newton's method in one dimension. What we did is we wanted to find the root of the tangent line, and we wanted to let xk plus 1 be the root of that tangent line. Well, that requires us to bring f of x sub k to the other side. So we now have a derivative times a difference equaling the negation of the function evaluated at x sub k. Well, if we let that difference be delta x sub k, then we're essentially solving this. In one dimension, isn't the Jacobian just the derivative of f? So it is. So we have a one-dimensional Jacobian times a delta xk equaling the negation of f evaluated at xk. Now, because it's not a matrix, we don't have to solve for a system of linear equations. We can just divide both sides by f prime. All right. So now xk plus 1 is xk plus this delta xk, which was what we found there. And so, in other words, xk plus 1 is xk minus f at xk all over the derivative at xk. All right, we've gone through the mathematics. However, let's look at an example so you can understand or visualize what's going on here. Here we have a vector-valued function of a vector variable. It's nonlinear because both u1 and u2 are squared. Now, on the right-hand side, we see f1, the first function, and f2, the second function described in the second vector entry. Now, as you can see, there is a gray plane that indicates z equals 0. Consequently, you can see that each of these functions is 0 along a curve in that plane. However, right here is a point where both functions are simultaneously 0. To begin, we calculate the Jacobian. So the derivative with respect to u1 is 2u1. The derivative with respect to u2 of the first expression is 2. The derivative of the second expression with respect to u1 is 3, and the derivative of the second expression with respect to u2 is 2u2. Note that if we evaluate this function f at the vector 0.75, 0.5, we get this result. That is, the first function evaluated at this vector u0 is 0.5625. Now, that's sort of close to the simultaneous root. Looking at it from another orientation, you can see that the second function evaluated at this initial vector u0 is 0.5, so slightly smaller. And once again, there is the simultaneous root from this orientation. Consequently, we see that this u0, 0.75, 0.5, is sort of close to a root. So let's use Newton's method to see if we can get a better approximation. Now, using the Taylor series, as we described before, we can find two tangent planes. So on the left-hand side, you can see how the red plane is tangent to f1 at that point, and on the right-hand side you can see the blue plane being tangent to the function f2 at that point. We want to find the simultaneous root of these two planes. That is, we have a system of two linear equations in two unknowns. How do we get to that root? Well, we find the Jacobian times delta x naught is equal to negative f at x naught. Substituting those values in, we have this system of linear equations, and we can solve for delta u naught. Having solved for delta u naught, we can add this to u naught to get our second approximation. So that simultaneous root is our second approximation, u1. If you calculate it, that's u1, and if we evaluate the function at u1, we find that both values have a significantly smaller value. That is, we are closer to the root. Well, now that we found u1, we can do the same process again and find u2, u3, and so on and so forth until it appears to converge. So here's the sequence of iterations. From u0, we saw that we can calculate u1. If we were to repeat this process and calculate it again, we would find this point here. Notice that there's approximately twice as many zeros there, so it seems to be converging at the same rate as Newton's method in one dimension. After one more iteration, we see that we have a very good approximation of the root because, again, the value of the function is almost 0. Now, to 16 significant digits, the root is actually closer to the value on the left. However, if you'll notice, after only 3 iterations, we have 8 significant digits. That's pretty good. So following this topic, you now understand the generalization of Newton's method. In 2 dimensions, we have 2 expressions, nonlinear, in 2 variables, and we want to find a simultaneous root. So given an initial approximation of that simultaneous root, we find 2 tangent planes and find the simultaneous root of those 2 tangent planes, and iterate. You now know that this generalizes to n dimensions as well. You can find the tangent hyperplanes, again using the Jacobian, and find the root of the tangent hyperplanes. You are aware that this has convergence that is still order h squared. Now, the coefficient out front has to do with a matrix called the Hessian, but that is beyond the scope of this course. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!